This is a bit awkward. Shouldn't the compiler already know that you are iterating? You are in a for loop after all. In Java 5, the enhanced for loop now supports collection objects. You no longer need to get an iterator. In the following revamped code, a for loop iterates through the list and prints out each value. The for loop defines a local variable called item, which gets assigned the next value in the list during each iteration. Besides the beautiful for loop syntax, there are two other ways in which this code is different than the old Java code. Generics. The syntax above with the funny angle brackets is new to Java 5. Generics let you define classes that work with some specific type of object, but the type is not known until you create an instance of the class. The compiler will enforce the type restriction. In our example, the array list is a special one that accepts only integers for the add method and returns only integers from the next method of its iterator. This means that no casting is required when objects are retrieved from the list. They can immediately be targeted as integer instances. Without using generics, you could still use the new for loop syntax, but you would need to cast from object to integer. Generics will be treated in more detail in the section Generally generic, writing methods with generic parameters. Integer int equivalence. In Java 5, an integer object can be treated as an int. The compiler will automatically perform the conversion from int to integer object, and vice versa. This process is called autoboxing. When we retrieve the item out of the loop as an integer, we can add it to an int value without doing an explicit conversion. The new for syntax also works with arrays. This new syntax certainly makes the code a lot more readable and compact. Unfortunately, you can't completely throw away your iterators yet, at least for a while, because there are still many developers who have not upgraded their GTK to version 5. Let me count the ways using the Enum. Most applications need to keep track of a finite set of values. Constants that represent a set of choices or states in the application. One common Java programming practice is to use static int variables to represent these values. Programs then make decisions by comparing the values of other variables against them. Although the core Java API itself uses this practice, it can lead to serious problems. The following example class returns information about fruits for an imaginary menu planning system. It shows some of the problems in using int variables to represent enumerated data. The durian fruit, which comes from Southeast Asia, is both smelly and sweet, but we will assume in our system that fruits can be only of a single type. That is, all values are assumed to be single values rather than composite ones. The main problem here is that any int value can be passed to the getCategory method, whether it is a valid fruit or not. This can lead to subtle bugs, since the compiler will not care if you call getCategory sweet or even getCategory 42. And if the values of the integer constants ever change, the meaning of the category getCategory 3 may no longer be obvious or correct. A different problem is that there is no distinction between the use of int values for fruits and for categories. They are all just plain old int values. You could partially solve the fruit category separation problem by simply placing the category constraints into a separate class, but they are still just int values and are not type safe. Nothing restricts the parameter of getCategory to a fixed set of values. In Java 5, there is an elegant solution. You can create enumerated types, just like in C. This is a new feature which creates a class that contains a list of all its allowed instances, other than what is defined within the Enum. No other instances are allowed. To take a close look at some Enum examples. Each of these examples define a separate group of enumerated elements choices. The beauty of this is that the fruit value cannot be mixed with or confused with another type. Each enum is treated as if it were a different class. You cannot pass a fruit category as a parameter to a method that expects a dessert, nor can you pass an int value. Let's expand the fruit enum to include the functionality of our original fruit constants class. Notice that an enum can define methods just like a class. The getCategory method now takes a fruit as a parameter, and the only allowed values are the ones defined in the enum. This next code snippet would cause compile errors rather than unexpected runtime results that would have occurred In calling the original unprotected getCategory method, it would be better if each fruit managed its own category. So to compile the fruit class, we'll now remove the fruit parameter of the getCategory and make the method return a different value for each enum state. We can do this by creating an abstract getCategory method that applies to all the values and override it differently for each enum. It's very similar to writing a different subclass for each enumerated value and having each of those classes override the abstract method. Once you create an enum like this, you can treat an apple value like you would any other object using the static fruit.apple reference, and you can call its getCategory method to get the associated category. We can now add a main method to the above class and show how to use the new fruit enum. As this code illustrates, you can use the value method to iterate through all the values within the enum. The toString method of an enum will return a string with the same name as the value, using an enum to represent state instead of an int can make your code much more readable as well as more error resistant. It certainly defines all the values for particular enumerated state and prevents someone from using inappropriate values. Practice safe putting using type safe maps. We saw earlier during the for loop discussion how using generics can help to make your code simpler and less error prone. The for loop was able to assume that the array list contained only integer objects because we defined the array list as consisting strictly of integer objects. We could then avoid the casts from object to integer as we retrieved item from the list. Java 5 made many changes to the core API that take advantage of generics. Looking at the documentation, you will see that many of the classes are now redefined so that generics can be used. If you wish, you can still construct and use any of these classes the old way. For example, new array list. This might be done for compatibility reasons so that your code would still work under older versions of the compiler. Of course, you would then lose the convenience and safety of the type checking process provided by generics. One class that has been nicely revamped in Java is Java util map and hash map. You may recall that maps work like lookup tables, with each value stored under a unique key. In earlier versions of Java, when you place items in the map, they go in as object entries. As you retrieve an item from the map, it is treated as a standard object reference, which you must cast to the appropriate subclass in order for it to be recognized as its true type. The same dangers apply here as in a list. The object may not be what you assume. And class cast exception is the unfortunate result. How many times have we seen those? Imagine that we have an employee class for maintaining employee data. It is some typical code for working with hash map. The biggest danger is during the cast, when the item is retrieved. With Java 5 you can do without a cast, as long as the map was instantiated with the correct type. You can add a constraint on the types of both the keys and the values. In the example below, only string keys and employee values are allowed. By using type-safe maps, you can avoid class cast exception problems when retrieving item from a map. This makes your code much more stable and less sensitive to the contents of the map. Unfortunately, if your code has to run on earlier versions of Java, you are out of luck, and you'll need to keep on casting for a while. In the next section, we create our generic class. Generally generic, writing methods with generic parameters. We saw in earlier sections how generics can simplify Java code and make it resistant to class cast exception problems. In addition to using generics that are part of the GDK, you can write your own. This is useful when you are working with objects that are all of the same type, but you don't know which type it will be until you instantiate your class. This is ideal for classes that have an associated collection of items or involve a lookup. Let's write a method that uses generic parameters. Recall how we used the ArrayList class earlier. Only when we constructed the ArrayList did we specify which object type is used. We don't know the type when we are defining the class, and we can't use java.lang.object as the type, because we would end up with the same casting problem as before. When you define a generic, you must use a specified syntax to stand in for the type. This is done when you declare the class name in the following example. T presents a type that will be used by our class. The type indicator brackets looks strangely like HTML syntax, but actually have nothing to do with HTML. Nor do they indicate less than or greater than. The angle brackets are used in cases where a generic's class name is combined with a type, as in the ArrayList integer that we used earlier, although the real type will not be known until the constructor is called. We can use the substitute type in our method definitions. We are really defining a class called random section. That works with another class of some type, which we will call T for now. The name of the class is still random selection, however. By the way, you can do this for more than one type at a time, as the definition of java.util.map does. In these cases, use a comma-separated list of identifiers after the class name. The myGeneric class defined above works with three classes, and we are calling them T, U, and V. Let's expand the random selection class by writing a method that adds an item to an internally managed array list of the generic type T. Remember that we are not actually dealing with a class called T. Instead, T is a stand-in for whichever class is used when someone creates an instance of random selection. The Java specification allows you to use any identifier that you want, but the standard convention is to use a single uppercase letter to distinguish it from a normal class name. Now that we have defined the add method as taking a type T parameter, it can be called only with the same type used in the construction of the random selection instance. The following code is illegal and generates a compile error. If you want to return a generic type from a method, you can use it as the return type of the method's signature, as the definition does.